Hello, my name is Dr. Randy Feldman, and welcome to the wonderful world of orthodontics. What I'd like to show you, which is really interesting, is the biomechanics of how orthodontics works today. As I explained earlier, what orthodontics is a system of very, very small metal squares called brackets, which we simply glue onto your teeth. Once we have them on your teeth, people ask, well, how do teeth move? Well, nowadays we have space-age wires that were developed during the space program. They're made of nickel and titanium. Therefore, they're called NiTiNol, nitinol wires. Ni stands for nickel, Ti titanium, NOL stands for Naval Ordnance Laboratory, and they're developed in Iowa by Dr. Andreessen in the early 70s for the space program. How do we use that wire? We actually engage it into the brackets, where you take someone that has very crooked teeth, like this situation right here, and then you can use the memory of the wire, also called memory wires, to make their teeth straight and lined up like this. So how do we do that? Well, we take this wire, which is made of nickel titanium, and we go ahead and freeze it. So we'll put some spray on it right like that. You can see it's already getting soft. It's becoming dead soft. Therefore, we can put it in your mouth and it doesn't hurt at all. See what it is? But what will happen during the day, the heat of your mouth will warm up the wire, and you can see how it bounces back to the exact same shape. We use the same memory wire, and we engage it in the brackets, and then as your mouth warms up the wire, it makes it flexible and goes back to its original shape, therefore straightening your teeth.
This spring fascinates me. I'll completely uncoil it, except for a few kinks. Now, watch as I put it in hot water, 75 degrees or so. Rapidly, the spring reforms. Let's watch it again, but close up. I stretch the spring, and then, to slow down the action, use a hairdryer to heat it. This spring is made from nitinol wire. The name comes from the elements it contains and where it was discovered: nickel and titanium and the Naval Ordnance Lab. It's showing what's called the shape memory effect. A length of this wire was formed at very high temperatures into a spring. This shape setting occurs at temperatures above about 500 degrees Celsius and then cooled. Almost no matter how it's bent at room temperature, it returns to its original shape when heated at 75 degrees Celsius or so.
One of the more polluting productions in the world is concrete structures. Over the years, tiny cracks form in the concrete, and to make sure the structures don't collapse, there is a need for even more polluting concrete production for maintenance. Researchers from Cardiff, Bath, Bradford, and Cambridge joined together in an adventure called Resilient Materials for Life, RM4L. And they came up with an interesting idea. Instead of adding more concrete into fixing the structure, what if the concrete would fix itself? RM4L is developing 4 main types of self-healing concrete methods. In the first method, microcapsules containing a healing agent are being developed to be mixed into the concrete. If a crack forms, it will rupture the capsules, releasing the glue-like agent that will glue together the microcracks from within. The glue agent is also used in the second method. Tunnels are built into the concrete, with glue pumps attached to its side. If a crack forms, sensors signal the pumps to release the glue to fix the damage. The third solution is a shape memory polymer that's shaped into tubes and built into the concrete. If a crack in the concrete deforms the tubes, sensors placed inside the concrete will detect the damage and activate the polymers by heating them up, so the polymers contract to their original tube shape and pull the concrete together. The last healing method is by the inclusion of dormant bacteria and nutrients in the concrete mix. If cracks form and water penetrates the concrete, the nutrients are dissolved and the bacteria start feeding. This results in the precipitation of calcium carbonate by the bacteria and leads to the sealing of the cracks. The bacteria can also heal historical buildings and monuments. Self-healing concrete could be one of the solutions of tomorrow to reduce concrete-based pollution.
Discover what's possible when we think research at Case Western Reserve University.
You find a nasty scratch on your new car. Now what? This research team at the Case School of Engineering may have just found the key.
We came up with this idea to basically develop a coating that if it was scratched, you could simply take out a light and heal the scratch.
Stuart Rowan's engineering team had already developed a material for a separate use, but surprisingly had all the necessary components for this endeavor.
Just as a quick experiment, we took out a razor blade and deliberately scratched the material and then put it under a UV light. And within 30 seconds, the scratch had disappeared. That was the eureka moment. That was like, wow, we've got something that's really cool here.
So, what's the scientific secret?
So what we've developed is essentially a new plastic material composed of very small chains that stick together and assemble into much larger chains. But what we've designed into the molecule is essentially the ability for it to disassemble on exposure to light. When it disassembles, the material flows into the crack and the system gets healed.
And the discovery is just scratching the surface of possibilities.
What you can imagine is essentially a new paint coating on your car that you can heal whenever someone's rubbed a key down the side of it. Another one is this could be a new varnish for your dining room table, where you get a scratch on your table that can be easily removed.
The next step is to use the proven concepts to design a commercial coating tailored for specific uses.
Because it has such interesting applications, we've had discussions with a number of companies on how we might be able to translate this out to the public.
Learn more on how Case Western Reserve University thinks beyond the possible at case.edu.
I'm David Lussey. My company is Peritech, and we've been working with Young Foresight here in the Northeast. Even the smallest inventions have a big impact on all of us. We have invented a brand new substance called QTC, and this is QTC. It's like black rubber, but it isn't. It's a conductive substance which works under pressure. If I put it against these contacts, you can see that I can control lamps and other electronic devices just by pressing on it. QTC has billions of tiny conductive particles within it, held together in a plastic. These particles never actually touch, but when you move QTC or put any sort of pressure on it, they come closer together, and that alters the flow of electricity between them. QTC allows us to design things in a different way. This is a power tool with QTC panels on it. These now replace the on-off switch and the speed control, because when we touch these panels, it switches on the tool and we can alter the speed by pressing them harder, like this. That's the power tool of the future. QTC can be put onto any surface to make it touch sensitive, but you can put it into textiles or clothing. And when we do that, we call it soft switch. And down here, I've got a soft switch piano. And you can see it's made with a textile. But the difference is, when this one gets dirty, you can throw it in the wash. My challenge to you, using QTC, imagine what products or services you could design for the future.
In some sense, this everyday watch isn't special at all. I mean, I bought it for $10 at Target. Yet once we look inside, it's amazing. Let me show you. I'd call it the key machine of the modern industrial age. Precise timekeeping made possible things like the global positioning system and our telecommunications infrastructure. Now, this metal container holds the heart of this watch. Inside lies a tiny quartz tuning fork. I have one. Now, it's so tiny that I keep it in this white cap. You can see it right there in the center. Now, although this modern circuitry is vital to the watch, it's based on the same principles of the first clocks built in the 17th century, resonant motion. It's easiest seen in the pendulum clock. This family heirloom, it hung in the living room when I was a kid, uses the motion of a pendulum to keep time. Now, this pendulum oscillates with a regular period that runs a clockwork that translates this motion into movement of the hands. There are many ways to create resonant motion. For example, a tuning fork. This one vibrates 440 times a second. That's an A note when struck. I love that sound. Now, if I slow down the motion of the fork, you can see how the tines move back and forth with a regular period. That's resonant motion, like the pendulum, which can be used to measure time. The quartz crystal I showed from inside this watch is a tiny tuning fork. It vibrates at about 30,000 times per second. But how do you get it to vibrate, and how do you measure its vibrations or record its vibrations? I mean, we cannot get a hammer in there to hit the quartz crystal. The engineer who designed this digital watch used something known as the piezoelectric effect to make the small tuning fork vibrate. You can see this piezoelectric effect most easily with Rochelle salt. Here at the center lies the crystal. I've attached 2 electrodes made of tinfoil and strung wire from them to a small bulb. Watch what happens as I strike the crystal with a hammer. As I deform the crystal, it generates a current. The reverse also happens. If you place a voltage across the crystal, it deforms. This is how the quartz tuning fork in the watch is pinged. A voltage from the battery sets it in motion, and then the watch's circuitry measures the current fluctuations that represent the resonant motions of the tines. Quartz is ideal for digital watches because of its outstanding physical hardness and mechanical and chemical stability. And that stability makes this watch work nearly anywhere on Earth and under all but the most extreme conditions.
Piezo buzzers work kind of like a drum. The drum has a membrane that is struck by a drumstick, causing it to vibrate and produce noise. However, in a piezo buzzer, the drumsticks are replaced by an electrical current. As the electricity flows through the buzzer, it goes through in a ceramic material with piezoelectric properties. This means that when voltage is passed through the material, it vibrates, producing a noise. We can change the frequency of the noise by changing the frequency of the electricity. Thanks for watching.